We're having 3 more presentations on this session, and it's going to be about post-quantum protocols and agility. So I invite the first speakers to come to the podium for the presentation, Stefan and Sophie. 10:35. Yeah. Okay. Let's wait 5 more minutes. We're going to be talking in this session about post-quantum cryptography in protocols and agility. And I have the pleasure to introduce the first speakers for this session, which is Stefan Kubel and Sophie Schmidt. Schmidt is going to be talking about cryptographic agility and post-quantum cryptography at Google. So Stefan or Sophie, if you can approach for your talk. Okay, so thank you. We have, as I said, Stefan and Sophie, who are going to be talking about cryptographic agility and post-quantum cryptography at Google. So take it away.
Yeah, thank you. And thank you everyone for coming. Yeah, in this talk, we will talk about 2 aspects, like one is crypto agility, the other one post-quantum cryptography. And I'd like to start on the crypto agility part and look a bit back like what we said previous RWCs, we had various talks on different aspects of how we do crypto agility at Google. And all of these together kind of form different puzzle pieces on how we do that. So we had like a talk in 2018 on how our internal key management system works. In 19, we had a talk on our cryptographic library Tink. And in 21, we talked about what's in a key. And in this talk today, I want to talk a bit more about sharing some difficulties we have with crypto agility in practice and how we address them. But first, yeah, what are like the main goals for crypto agility for us? So one of the most important things for us is we want to enforce best practices so that all developers at Google can do the right thing when they use our cryptographic libraries and key management systems. So for instance, we don't want people to make bad choices on algorithms. We don't want them to like choose IVs. So there's a lot of different ways we try to achieve this. But on the other side, yeah, we also don't want to burden the users. Like to enforce the best practices, we don't want the users to have to take, like for instance, keep track of which keys they are using or do key rotation manually. So it's really important with the scale we work at that developers can use cryptography in the correct way without too much hassle. And last but not least, reliability. So with key management, like if the keys are not available, services go down. So reliability is very important here. And today I mostly want to talk about one best practice, which is key rotation. And in particular, our goal is that key rotation happens automatically. So this has a lot of advantages, because if you can do key rotation automatically, yeah, you get forward secrecy. But also, should a key have a leak, it allows you to recover in with much less operational risk. Because if your keys already rotate automatically, it's much easier to move away from a compromised key. And also, it becomes much easier to switch keys. So if we can automatically rotate keys, we can very easily switch to like different type of algorithms. And this is very important, like for instance, if you want to transition to post-quantum algorithms. Like if you have automatic key rotation in place, rotating the key is mostly about whether you can take the performance hit. However, in practice, it's not so easy to enforce automatic key rotation. So there's a lot of reliability risks, because if you rotate keys, key material might become unavailable, and that can cause issues in practice. However, I would also like to highlight, if you don't do automatic key rotation, you have a much higher risk. Like for instance, if a key is compromised and you don't do automatic rotation, it becomes much harder to move away. So by not doing this, you basically are shifting your problem to a later stage and accumulating technical debt. So from a user perspective, how does this look like? So our users, which typically is our developers, they have to set up like, which key type do they want? Do they want to encrypt data? Do they want to sign data? They can specify like key formats. They have to specify like, for how long do they need the ciphertexts, and also for how long do they want to cache the keys. But for instance, generating this key material, distributing it, and also rotating the key material is all taken care of by the key management system. So when a user has set up a key, well, they only have to do two simple steps. Well, first they have to retrieve the key. And when I talk about your key, it's typically a set of keys. So we usually abstract this away for the user. So every time I talk about a key, think about it as a set of keys. And for this, there's like the authorization and authentication is typically based on the service identity. And we also do something binary authorization, which is very interesting, but a topic for another talk. And then they just use the key in the library. And the nice things are our cryptographic library Tink. It handles a lot of things for the user. So the user doesn't need to know which key inside the keys that they have to use. They don't have to think about refreshing the key material. The library takes care of this. And the library also supports that you can have in a key set keys of different format. So you can, for instance, have your ECDSA key in there, but then also add your dilithium key later. Now I want to do a quick discourse to the NIST key management standard, which is a very nice standard on how to do key management, but it's also fairly complex. So for instance, it defines like 6 different states, and there's 15 possible transitions between these different states. So this is a very complex process. And I just want to briefly go over 3 steps to highlight some of the problems we see. So the first thing is like, when you generate the key material, actually it's not, you cannot actively use it. So first you have to ensure this key material is available everywhere. So you have this problem like, when is it safe to start using this key material? And in the next state, now we start using this key material actively. So we use like this golden key for that. And then you really use the key material for encrypting data or signing data. And it's very important, you have to ensure like all other parties which process the data, which is encrypted with this key, have this key available. And the next step in the lifetime of a key is typically that it becomes like suspended or deactivated. So here the key is not used to actively encrypt any new data, but you only decrypt data with it. But then there comes the problem, at some point I would like to delete this key. I don't want to keep keys indefinitely, because this will increase the risk if the key set should ever leak. So very simple example, let's assume we have like 2 locations. So we generate a new key, then we have to ensure it's available in all other locations. And then we can make it active. So if we then want to rotate the key, again, we have to generate a key in all locations. And then we can make it active and make the other key inactive. And again, we have to propagate this. So this is very simple. Again, we rotate the key, generate a new key, and at some point we can delete this key. Now, unfortunately, in practice, it's not that simple, and it looks more like this. You have like many, many different locations, and at each location, many instances of a service might access this key. And this might be even more complicated by, for instance, public keys. Like some services might only need the public key, some need the private key. And overall, the whole key management becomes a very large-scale distributed systems problem. So what can go wrong with this? So here's like a very simple, we have two services. One is used to sign some URLs, which are then given to the user. Then the user accesses this signed URL and another service verifies this. So like if both services have the key set in the same state, everything goes fine. But let's assume the service A now rotates the key and makes it active, then verification would fail if the other service doesn't have the key set in the same state. So this might look very trivial, but actually there's a lot of different root causes why this verification might fail. So the obvious one is like, yeah, like service P fetched the key set in a different state. But this can happen also because maybe the KMS didn't propagate this key set state in the timely fashion. Or maybe service P is on a different, is fetching the keys at a different time point than service A. And it's also not possible for the service, like on each operation, to fetch the key set because this would add a lot of latency. Also, maybe the user holds the URL for a long time and the key set's changed in the meantime. So yeah, a lot of different possibilities this can go wrong in practice. And the scale of this problem is huge. Yeah, so we have like thousands of teams setting up their keys. They work on different release schedules. They have different use cases and needs. And the use cases, they vary from signing maybe every couple of weeks up to like 1 billion times a day. So we kind of need a solution which like addresses all these different factors. And so one key improvement we recently made is that we added like horizontal monitoring directly in our cryptographic libraries. So this achieves two things, like we can keep track of like in which state the key sets are, but at the same time we achieve that they do not burden our users. So the users do not have to keep track of this. So the challenges here are quite big. So first of all, latency. Like if we do this directly in the cryptographic library, operations have to be really fast. So imagine you just encrypt a few blocks of data. You cannot afford any overhead really. At the same time, you also have a very large data volume here. So you really need to carefully think about how you aggregate the data to make it handleable. And also, yeah, the integration in the crypto libraries. So the crypto libraries, they are available in many programming languages, and you need to integrate this monitoring everywhere. So how does this look now? Yeah, from a user perspective, so if you have like service A and service B, the nice thing is for them, nothing changes. So the developers just still, they fetch the key, they use the library, and they don't have to make any changes. But on the back end, we now get the information like in which state the key set was when they did a certain cryptographic operation. And this allows us to improve reliability of key rotation because we get like useful signals from this, like for instance, when is it safe to make a key active? Or also when can we delete a key? So we know exactly like, is like this inactive key still being used anywhere? We can also notify the teams if they violate. For instance, I mentioned they set up like, how long do I need my ciphertext to be available? But by directly monitoring in the cryptographic library, we can now know, are they holding up this contract? And also, we can also block, in the worst case, the key rotation if we notice someone is still actively using like this old key material. So apart from this key rotation case, like this horizontal monitoring, actually, gives us a lot of other nice features we can do now. So it allows us to enforce best practices. For instance, there are a lot of encryption modes which have like a very low bound on the number of queries you can do on the key. And if you look like at this, if you remember this world map of like many services, for instance, if you want to answer, is any key used for more than 2 to the 32 queries? This becomes very hard if the services would have to manage this. But by tracking this directly in the library, we can now answer questions like, is anyone using a GCM key with more than 2 to the 32 messages? It's also very nice here to detect like usage of legacy keys or guide replication, because we can exactly see who is using still which algorithms. And it's also nice, like if you're migrating from one algorithm to another, we can observe this in the monitoring. We can see like which percentage of a service already moved to the new key. Which brings us to the second part of this talk, which will be about how we transitioned one of our protocols to post-quantum.
Yes, thank you, Stefan. And as Stefan mentioned, I will go a bit deeper on how we do post-quantum cryptography at Google, especially about a specific thing that we did to our encryption in transit. So why is it important to talk about post-quantum cryptography now? The main risks that we have is like for encryption in transit, store now, decrypt later attacks, which means that an adversary doesn't need to have a quantum computer right now. They can store the ciphertext of something that they're interested in the future and decrypt it at a later date. So this means that if we want something to be kept secret for 10 to 15 years, we need to start on this migration now. This gives us the priorities to like, if we want to do PQC in practice, the first thing that we need to do is encryption in transit. The second thing that we need to do on a fairly similar time scale is signature schemes in the case where the public key cannot be changed. The main example there is hardware roots of trust, where the firmware for the hardware root of trust has a signature on it that was burned into silicon, which will mean that yeah, you need to have that now if you want your device to live for more than 10 to 15 years. The rest of it is all other asymmetric cryptography, mostly meaning signature schemes. Signature schemes are not as vulnerable to these store now decrypt later attacks because I can just change the scheme when the quantum computer arrives. We also cannot forget about like the other primitives that are like the more fancy asymmetric cryptography. We see some other talks about this topic later. Lastly, there's also symmetric cryptography that is only attackable by Grover's algorithm, and as the research right now looks like, it's not likely that symmetric cryptography can be feasibly attacked by a quantum computer in a reasonably short time frame. So symmetric cryptography is somewhat out of scope for us at this point in time. So when I talk about encryption in transit, what do I talk about? There's this famous diagram of our internal infrastructure that was like disclosed to us by an external security researcher and pointed out over a decade ago that, hey, some of this traffic is in clear text there. So what did we do? We fixed this problem that was reported to us and came up with our own scheme called ALTS. Why not MTLS? Well, A, that was over a decade ago, and B, a lot of these services have very strict requirements for latency. So we needed to have something that is very, very optimized, very clear on what it does. And since we control ALTS completely in all its implementations and so on, this is the point where we can start experimenting with PQC and get to this state here where all our internal communication is protected against quantum attacks. So how does ALTS work? I want to give a very quick overview here. There is a white paper on this available if you want more details. I will focus on the part of the protocol that happens when forward secrecy is not a requirement, which is used for the very latency sensitive use cases. So how does it work? Essentially, it's a static to static ECDH key exchange and fairly straightforward from that point. So in the first message client init, the client sends its static ECDH key along with its certificate for this key to the server. The server will then respond with its own static ECDH key and a certificate for that static ECDH key. And since the server now has all elements that it needs, it will also send a secret confirmation message and like allow the client to check that the shared secret was computed correctly. The client responds to that with its own secret confirmation message and sends its own MAC back to the server. At that point, both server and client know that they're talking about the same shared secret, so there should be no monster in the middle. A slight variation happens, which is extremely important for the low latency use cases, when the client has a resumption ticket. So when the client has a resumption ticket, the client will just send this resumption ticket to the server in client init, and the server can just check. It will also still send the static credentials just in case the ticket is invalid. If the server accepts this ticket, it will replace the whole shared secret with whatever is in that ticket. So you don't have to do any asymmetric cryptographic operations in this case. And the whole thing is very efficient using only symmetric cryptography. So what are we going to do to this protocol now? This is like a bit of an approximation of what the sizes of these things are. You have a key share, you have some protocol overhead, you have a certificate. I used a single ECDSA signature. I'm not actually sure if it's one or multiple or whether there's an RSA, but you can see roughly how large that thing is on the wire. And then, well, we added an HRSS public key or ciphertext to this message on the wire. Why is it HRSS? We started the whole project in 2020. That was long before NIST came up and decided on Kyber for the standard. We will eventually migrate to Kyber, but for the moment we had an HRSS implementation lying around, so we were just using that. Yeah, so what do we do with that? Well, we just added ephemeral to the client in its message, and the server will then encapsulate to this PQC public key and send the ciphertext along with it. The problem is that this was a non-starter from the very beginning, because now the client has to generate this very costly to calculate PQC key on every connection, even if the server doesn't even speak PQC, so we can't even start rolling it out like that. So the first modification was to cache this client key a bit so that the client wouldn't need to reuse it all the time or recompute it all the time. Then with that change, we were able to start the rollout and ran into the first few problems. Like one of the problems was that when you like we initially allocated the HRSS key and related objects on the stack. That led to some workflows and architectures having a literal stack overflow because it was just too big. So we needed to put that on the heap, but still our rollout needed to basically start from the beginning again. The other thing that happens is as this ramped up, we then get more and more connections that actually start using this PQC model. And we did benchmark testing before, and we benchmarked it to, and it said to a bit of our surprise that we would actually be in the latency requirements, even in those cases that are supposedly latency sensitive when doing that. So we just started the rollout like that with Resumption doing the same kind of ephemeral key exchange as well. It turned out that the benchmarks were wrong. The main reason was that the allocation behavior of a benchmark is very different to the allocation behavior of a fully rolled out system. And so the problem wasn't actually like the actual computation time that we had, but the other stuff around it with allocation behaviors and so on, making it so that the latency was substantially higher than what we had previously thought it would be. But that's also somewhat straightforward to fix. You just don't do that in these cases because the resumption secret is derived from a secret of an earlier key exchange. So presumably it's already quantum secure. So you don't have to do that as long as you don't care about forward secrecy, which in these cases we made the decision to not care about them to begin with. So why would we do the ephemeral parts here in this resumption case? So with that fix, we then actually were able to roll it out and not cause any further production problems. So what are the takeaways of this? First of all, when talking about PQC in practice, it's very important to threat model things because these things are expensive, these things take a long time. We need to make sure that we invest our resources in the best way possible. And that means the highest priority should be encryption in transit and these aforementioned signature schemes where the public key cannot be changed because it's burned into silicon somewhere. And in those cases, you can argue that we are actually a bit late on the timeline because we actually do care about some data for more than 10 years. So we should probably get on with PQC rollout. The next thing is that the hybrid deployment method actually allows us to experiment rather freely with PQC because in the worst case, well, we learned some things, hopefully didn't cause any production outages, but we didn't do anything of value. In the best case, we already mitigated store now decrypt later, so it's a nice bonus to have. And lastly, rolling out PQC takes a long time. Like we started this work in 2020. We are now finally getting to the position that the last few jobs should start using PQC only. And there were many unforeseen obstacles. Like I don't think that I expected a Stack Overflow to happen without an array out of bounds read. Yeah, so this migration will take a long time. This was like the first of many things that need to migrate. So we should really start with this migration sooner rather than later. And with that, I would like to thank you for your attention and open the floor for questions.
Thank you very much. I see already Nigel for a question.
The talk, as I understand it, to do the key management, you're instrumenting when the users use the crypto, and that helps your key management, yeah? Yes. Okay, right, okay. So let's put aside encryption in transit, because that's kind of easy. But for encryption at rest, if I have an encryption key, how do I know how long the data is going to be there? Is the ciphertext, in some sense, do I look to see whether the ciphertext is still on the system, or do I say when I generate the key, you're only allowed to, you can encrypt stuff, but if you try to decrypt it after 3 years, then that stuff will just automatically disappear? How's that kind of instrumented?
Yeah, so it's a good point. So usually the services would re-encrypt on a regular interval to address this issue. But exactly, you have like this issue, like if this ciphertext is not in your control, it becomes very tricky. Because maybe a user presents you a 10-year-old ciphertext, and it depends there how long do you want to have the key material around, and what trade-offs do you take. But typically on the services we control, where we have this ciphertext, we would just re-encrypt the data.
So when, still for the same first part, when you say that we monitor it and we know how to do that, is this like a high command type of service that does that? Is the center point that makes all these decisions? Is there an agreement to move to the next key? How any of that happens?
I mean, basically, so this happens the monitoring happens in the library, and the data which is exported from there informs the KMS. So the KMS would look at this and see, this old key is still used in this service. I cannot delete it. I will check with the service, why do you still use this key? And based on this, they would make an informed decision on whether they can rotate a key or delete a key or make a key active.
Okay, I don't see more. Oh, there you go. Go ahead.
So maybe a short question about the actual agility part. So I saw that you have HSSR in your application layer transport security protocol. Is there any form of negotiation? Like, can you replace now that post-quantum algorithm with something, or?
Yeah, like basically there is some form of like, I went over a lot of the ALTS specifics a bit quickly. There is a form of like which version of the protocol is being used, so you can change to Kyber later. I hope that that part is easy. So far, nothing about this project has been easy, but fingers crossed, it should technically be simple. But yeah, we'll know soon.
Thank you.
There's a question on the Zoom. If the only TLS ciphers were using a forward secret ciphers, can we delay the rollout of PQC implementation?
So I'm not sure if I caught the...
If the only TLS ciphers we're using are forward secret ciphers, can we delay the rollout of PQC implementation?
So, I mean, that depends a bit on what your goals are. These were jobs that were very, very performance sensitive. So if you look at the actual performance numbers of these PQC suites, they aren't that bad compared to like elliptic curves. So I think that in most cases where it's not like things that have to deal with like millions of queries in very short amounts of time, you are probably fine using your perfect forward secret cipher as you used to.
Perfect. I don't see any more questions in the Zoom. If you have more questions, approach the speakers later. And thank you very much for that talk. Next, we have Florian Vive talking about post-quantum noise. And your slides are ready, so take it away.
Yeah. Hello, so I'm Florian, and I will be talking about post-quantum noise. This is joint work with Yawning Angel, Benjamin Dowling, Andreas Hülsing, and Peter Schwabe. And except for Benjamin, the other authors are also all here. Before I start, maybe a short background on noise first. So noise is essentially a framework for, among other things, key exchange protocols. It also includes the messaging phase, but the part we were focusing on was the key exchange thing, where noise allows you to stamp out key exchange protocols depending on your use case in many different ways. And has many well-known users. You may have heard of some of them, like WhatsApp or WireGuard, Lightning, I2P. And in its original version, it's essentially Diffie-Hellman based. And this, of course, has many advantages, but a big disadvantage is that it's inherently vulnerable to quantum computers. And so let's still take a short look on how this works regardless. So essentially noise, in classical noise, we have static keys and ephemeral keys. A static key is a long-term secret generally used to identify yourself and get authenticity, though it can also give you some kind of confidentiality in the case of, well, in this case, Diffie-Hellman, later on key encapsulation mechanisms. And ephemeral keys, those are the short-term secrets that are there to, among other things, provide forward secrecy and post-compromise secrecy. And then the idea is to use many of these exchanges, Diffie-Hellman or CAMs, derive shared secrets and throw them into a hash chain. And so over the handshake, it will accumulate the several secrets in the hash chain and derive stronger and stronger session keys from it, and then use symmetric crypto to transport any further payload, which can, for example, if you have first an ephemeral exchange, be the static public key in order to protect anonymity, or in some cases you can also send actual message payload early at reduced security if you're saying, okay, this part of my interaction doesn't require the full forward secrecy, authenticity, or whatever. I'm fine with a reduced level there in exchange for better performance. And so since I said it's a framework, you have a lot, kind of an infinite number of possible exchanges there. And they are described as so-called patterns. And patterns, you see a simple example here at the bottom. So at first you have a label. In this case, this is the so-called XX exchange. It just means both parties have a long-term secret and the secret is not known to the peers. And then with these ASCII arrows, you indicate the message flow. So the left to right arrow means from the initiator, which is the first party that gets active to the responder, and the other arrow the other direction. And then you have these tokens. The E token indicates that an ephemeral public key is being transmitted here, generally as plain text. And with Diffie-Hellman, you can now combine various secrets. So for example, the ephemeral token of the initiator and the responder in this EE exchange. The first token identifies the secret of the initiator, the second of the responder. You derive your key, and then everything that follows is encrypted under a key that is, among other things, derived from that shared secret. And in this token, you then have the S, that's the static or long-term secret, and then you can combine the initiator's ephemeral and the responder static secret and so on, and you derive stronger and stronger keys to protect your interaction. And now our goal was, we want to have essentially the same thing, but secure in a post-quantum setting. And the most obvious idea you could have is, let's just replace all these Diffie-Hellman key exchanges with key encapsulation mechanisms. And for some parts of this works very simply. So if you have the ephemeral token, so the E, you just send an ephemeral public key for a CAM, or same for static public keys. This all essentially works as before. And then we introduced two new tokens here, the ECAM and the SCAM. ECAM means this is a CAM ciphertext that's encapsulated for the ephemeral key, and SCAM means it's encapsulated for the static key. And to somehow try to stay consistent with what noise does, ECAM tokens are ECAM ciphertexts are generally sent unencrypted, and SCAM are, if there is already a key, sent encrypted. And if you try this, you run into a few problems. So Diffie-Hellman is not just a CAM. It provides a functionality known as non-interactive key exchange, or NIKE. And that is much more powerful. It can, for example, be used to establish bidirectional authenticity. If you combine two static Diffie-Hellman public keys, you get bidirectional authenticity. And with a CAM, it's really non-obvious what to do there. You can also combine these Diffie-Hellman secrets freely, whereas with a CAM, you have a public key and you have a ciphertext. And if you try to use the ciphertext as a public key, I don't know what you're supposed to do there. There's no clear solution there. So let's look at how this turned out for noise. So some cases were actually still completely trivial. If you had the EE, so combination of ephemeral keys tokens, we could just replace it with an ECAM token. And similarly, if we had a combination of an ephemeral key and a static public key, and the receiving party of that interaction, so notice the arrows there, is the user of the static key, we can also use the SCAM token there. In this case, we view the encryption, the encapsulation randomness as an ephemeral secret of the sending party, and we get our CAM replacement. So that works without any issues. Then we have the case where it's being sent the other way around, where the sending party's static key is used and the receiving party's ephemeral key. And it turns out that if we try to translate it into CAMs, it's really non-obvious what to do there, because what this essentially means is I have my static public key and the other guy has an ephemeral secret, the randomness intended to encapsulate. And now I'm supposed to create a ciphertext that can be decrypted with that randomness. It doesn't add up. So the solution that works there is you essentially stop the pattern at that point and send it the other direction around. It's a bit brute forcey. It adds up to a full round trip, but it works. And then we have the really nasty case. That's the combination of the static public keys. So the first thing you can do there is you can send an SCAM in both directions so that you have an encapsulation for both static public keys, which gives you authenticity. but it still fails on one issue. If you're considering cases where the ephemeral randomness could be corrupted, for example, because you're using a bad random number generator, it's not like that never happened. The SS exchange will actually save you because there is no ephemeral entropy in there. So even if your random number generator fully leaks everything to the adversary, doesn't help them. Whereas if we send the chems both ways, we have an issue there. So we found a solution to cheat there a little bit. And overall, though, this works, but is not always the optimal pattern that you can get. So we also designed a couple of patterns specifically intended to be usable in the cases for which noise also gives some base patterns or fundamental patterns that cover the most common use cases. So I talked about we need to cheat. So there is this technique of combining the ephemeral randomness with a static secret. I think the first use case where this was used was the Nexus trick. Later on, there is a paper where it introduced a twisted PRF trick to do similar things. We actually have an RFC on a technique that is based on signatures. Interestingly enough, though, this was never introduced as its own primitive. So what we did in this place was to say, we introduced this as the primitive of static ephemeral entropy combination, provided a security definition there, and we now, with that security definition, we could then analyze the protocol for the cases where you do use it and where you do not use it. And if both parties use, or if at least one party uses static ephemeral entropy combination and you send an S-chem both ways, you are actually back to the point where you have confidentiality, even if you have a corruption of the ephemeral secrets. So ways to achieve this, there are many. The simplest one is you just throw them into a dual PRF function, essentially. We picked a slightly weaker notion than possible. That way, all the existing techniques are still applicable to us. And yeah, so that worked. And we can now get to the analysis of our results. So we were using the FACCE model because previous analysis of the noise framework had used that, and it's kind of designed for noise. It's specifically talking about the several stages in which the protocol advances and then specifies the security guarantees given. I think it's fair to say that many reviewers dislike this model. So anyways, in the end, we got accepted at CCS, despite it. And the other thing we did compared to this previous analysis of noise, so what we had until then was essentially an analysis of individual noise patterns. And a lot of this analysis followed the traditional approach of we replace each hash call or HMAC call with a PRF call essentially, and then have a security statement where you have this one point in there like plus 10 times advantage against PRF. But noise is not just using these hash functions randomly. There really is essentially an ad hoc hash object in there. So what we did there was to define a hash object where you can feed values in, and once you feed uncorrupted randomness in, all the outputs are essentially random. And that allowed us to do a truly generic analysis of noise. Now, one issue we ran into, the noise hash object does a bit of a weird thing at the end. One of the outputs at the last call is the thing that until then would have essentially been the state. So we actually introduced a noise pseudo-random hash object that has special cases there. I think Trevor already kind of hinted that maybe in future version this will be changed, because I've also heard from implementers they dislike these case distinctions. So with that, we could then analyze all arbitrary patterns, and we match all the previously proven security statements in the FACCE model, and we match the conjectured ones. As I said, the previous analysis didn't cover all possible patterns, so there are some unproven but very, very reasonable conjectures in there. I'd also like to note we treated all the key encapsulation mechanisms separately. So you don't have to use, say, Kyber in every single place. You can, for example, use Kyber as the ephemeral chem. And then if you have a situation where the static public key is already known to the peers, they can, for example, use classic McAleese, which in that setting outperforms essentially all the competitors and gives you what I sometimes call a poor man's hybrid scheme. It gives you hybrid security in the sense that if either Kyber or McAleese gets broken, you have still security, but under more restrictive corruption scenarios. So also, you can do it for performance reasons, or you can do it as like a very cheap way to hedge your bets against certain schemes. So slightly more specific, the results. If you use an ephemeral chem, so if you have the eChem token in your pattern, then after the eChem token, everything that is sent is confidential, as long as the ephemeral keys of both parties are uncorrupted, assuming you follow basic rules about how noise is supposed to be implemented. If you send a SChem, so static chem, you have confidentiality also from that point onward, as long as the encapsulating party's ephemeral key and the receiving party's static key is uncorrupted. And in the same setting, you get authenticity after one round trip. In this case, you essentially require a key confirmation, which is the cause of you sometimes needing an additional round trip, even with the optimal patterns, if you run PQ noise compared to noise, because with PQ noise, you have to do challenge response. With Nikes like Diffie-Hellman, you can sometimes avoid them. And then if you decide to use seek or static ephemeral entropy combination, then you can essentially take these statements, and everywhere it says that the static key needs to be uncorrupted for, that the ephemeral key needs to be uncorrupted, you can say alternatively the static key needs to be uncorrupted, which gives you the protection against the case where ephemeral keys are compromised, but you have an SS exchange in there. On the performance level, Yawning did an implementation in Nyquist using level 3 Kyber. And if you're looking at the numbers, so we have two patterns there. The first one, the KK pattern, is kind of the one that I described where the static public keys are known to the peers. And if you're looking at the numbers, both on a slow and a fast network, we are fully competitive with elliptic curve-based noise, in fact. In some cases, on the responder side, even faster because of how fast Kyber is. And the second example, the XX pattern, that's the one where you have transmit the public keys. This is also the pattern where you no longer can do a trivial replacement, but where you actually need a full additional round trip. You see still on the responder side, virtually nothing changes. On the initiator side, we do get a factor of 2 overhead, but still at what I would consider very reasonable timings. And yeah, with that, I'd like to thank you for your attention, and also Trevor Perrin and Denisa Krekonici for many helpful discussions we had.
Thank you very much for that presentation. Do we have any question from the public? I see none in the Zoom chat. If you have a question, please approach the mic. In the meantime, Florian, did you also benchmark the performance of the protocol with other suites that were not Kyber? Did you try other algorithms?
So I was not involved with that part. I think the only numbers we have right now is Kyber in that regard. But I mean, another aspect is that the network in many cases, of course, is a significant part of actual performance cost.
Could you clarify what went behind the process of choosing to rewrite noise with a key encapsulation mechanism rather than just giving parameters for a key exchange?
What do you mean?
Couldn't I just have done LWE key exchange with noise? What is the problem there?
So, I mean, for starters, the NIST process standardizes key encapsulation mechanisms, so that's kind of the primitive we have. I'm not sure that the RLWE exchanges can replace a non-interactive key exchange. C-side would be able to, And I'm told that all the breaks of isogeny do not affect C-side on a fundamental level. So if you feel very confident about the security of it, you might be able to replace it with C-side. But I have a feeling you're not going to find many friends if that's your approach.
Okay, thank you.
Last, there's a question on the chat. Is there any plans to support, I guess, in a more real world sense, hybrid class or PQ or post-quantum cryptography in noise?
So I'm not directly involved with noise. That being said, maybe I should have stressed this a bit more. The security results I've shown you, they really are standing on their own. It's if you have an SCAM or an ECAM token there, this is the guarantee we give you. This does not affect any security guarantees you get from also having Diffie-Hellman exchanges in there. So if you do non-composite hybrid, this is completely covered. We don't talk about the Diffie-Hellman guarantees, but we can fully assure you if you do what we are telling you in terms of the post-quantum part, you're getting the security. If you run a composite hybrid where you essentially have where your chem is not Kyber, but Kyber plus X25519, let's say. Of course, we only talk about it on the primitive level, so that also works. And if you want to run several chems, again, the statement we have about what ECAM and SCAM give you in terms of guarantees fully cover also repeated uses of these tokens. So I think we have a pretty strong coverage of hybrid security there.
Okay, thank you very much, Florian. Any other question, please find the speaker later. Next, we have the last talk of the session. That is okay. Next, we have the last talk of the session is going to be given by Guru Vamsi Polichala about post-quantum privacy pass via post-quantum anonymous credentials.
Thanks for getting my name right. Okay, so today I'm going to be talking about post-quantum privacy pass via post-quantum anonymous credentials. Okay, so I want to start with talking about what's the status of post-quantum crypto today, right? If we think about encryption and signatures, people seem to be reasonably happy with them. NIST has proposed 4 algorithms which are to be standardized. But the second you move past this, right, to a little bit more advanced crypto, let's think something like blind signatures or oblivious pseudorandom functions or even anonymous credentials, right? The situation doesn't really look so good there. So for blind signatures and oblivious pseudorandom functions, we have what I would call semi-practical constructions. By semi-practical, I mean, you can implement them, you can run them, you can get numbers, but they're still orders of magnitude worse than their classical counterparts. And for anonymous credentials, I would still consider the research to be theoretical because there's just no implementation. Okay, so what is the need for efficient post-quantum primitives like this? All of these companies that I've listed here, and even some companies in the EU, have deployed some variant of these primitives. And collectively, they're effectively impacting billions of users. So when you have such wide impact, you really want to migrate to post-quantum as soon as possible. So hopefully at the end of this talk, we'll be able to make some progress towards this. And for the case of anonymous credentials, we'll move from a theoretical stance to semi-practical. Okay, great. So let's dive in. I'm going to start by defining what a blind signature is. So let's say Alice has a message M, a server has a signing key SK, and now the goal is for Alice to obtain a signature such that the server learns nothing about the message M, and Alice should not learn anything about the secret key SK. There's going to be some interactive protocol. At the end of this, Alice is going to output a signature which verifies under the corresponding verification key. Great. So, suppose you had blind signatures. How are these companies and countries really using these things, right? A very common application is to authenticate in a privacy-preserving manner. What do I mean by this? I'll go in with an example. So let's say Alice wants to visit a website, right? She's going to go type in her address, but bam, she's going to get thrown with a CAPTCHA. Alice is going to be angry and frustrated, as I would be as well. And we're cryptographers, right? Is there a way to avoid CAPTCHAs without compromising privacy? And turns out if you're given blind signatures, you can. So what Alice is going to do is going to go to a server which the website trusts, So this could be Cloudflare, for example, and the reason this website would trust Cloudflare is because Cloudflare could be its CDN. So now what's going to happen is Alice is going to sample a random nonce TK, and she's going to get a blind signature on this. And what she's going to do is she's going to give a signature on TK to the website, and she's going to say, hey, look, Cloudflare would have only issued me this blind signature if I proved to it that I was human. And because you also trust Cloudflare, you should trust that I'm human as well. And then the website's going to say, OK, fine, you can access this website without solving the CAPTCHA. An important thing to note here is that a colluding server and a website is not going to be able to track a user. This would be very bad for privacy if instead of blind signatures, you just use signatures. Another thing that I want to mention is that this blind signature exchange can happen at the beginning of the day before you even know what website you're trying to visit, right? So you could just start your computer and be like, OK, let me just get a bunch of tokens, and your browsing experience is going to be seamless throughout your day. There are many alternatives and extensions to what I've described here. The first paper was at PETS in 2018. It was called Privacy Pass and used oblivious pseudorandom functions. But there have been many extensions. And alternatively, you can also use anonymous credentials. Anonymous credentials give you a bit more. I'm not going to go into the details of that, but they're also harder to build. OK, so how would you build a post-quantum blind signature? Let's say generically, right? This was an approach started by Fischl in 2006. And let's say now Alice has her message, right? So what she's going to do is she's going to create a commitment to her message, and she's going to send this to the server. The server is going to sign this. This is not a blind signature. This is just a regular signature. And the server is going to sign this commitment and send this over. So what Alice is going to do is she's going to generate a proof of knowledge, a zero-knowledge proof of knowledge of the following statement, which is she knows a signature on some commitment C, and she knows an opening R to this commitment C, which opens this commitment to M. And the final signature is just going to be this proof, and she's going to output the message. OK, and one thing I want to mention here is that using this exact same approach, instead of signing your message, you sign a bunch of attributes, you can get anonymous credentials. And the advantage of this is that when you sign a bunch of attributes, you don't have to reveal all of them. So for example, think you're signing your passport, right? What you could do is instead of revealing your exact age, you could say, oh, I'm greater than 18, so I can buy alcohol maybe. OK, so how do you instantiate this primitive, right? We want to build post-quantum blind signatures. So the commitment, the signature scheme, and the proof system has to be post-quantum, at least to be plausibly post-quantum. OK, so there's been prior work in this space. We're obviously not the first ones to look at this. But the general consensus was that if you just throw a general purpose proof at it, right, it's going to be too big and too slow. This is a quote from a paper at CCS 2022. And they said that they expect the prover runtime to be at least 1 hour if you just throw an off-the-shelf proof at it. And the strategy in essentially all the works that have been in this space is to say, look, there are some expensive parts in the statement. This could be hashing and a bunch of things that are not really conducive to zero-knowledge proofs. What we're going to do is move it outside the statement. And this is quite non-trivial. Sometimes you have to introduce new assumptions or just be very careful with the security reductions to really get good parameters. But this comes with a caveat, which is you can't directly use these approaches to get anonymous credentials. And intuitively, the reason is because in these optimizations, what they do is they say, look, if you're anyway going to reveal this message to the verifier, you can actually ask the verifier to do some of the expensive computation in the clear and not actually prove that. And that allows them to offload a lot of the expensive computation outside of the proof. And essentially, the proofs you need are very simple for linear relations and, again, very impressive works. But, let's say you really wanted anonymous credentials. So we asked the following question, right? What if we just carefully chose the signature scheme and the proof system, and we really optimize it to death? How expensive are these anonymous credentials really going to be? Turns out, we were surprised by the numbers ourselves. So the prover time, in the best case, can be as low as 1/3 of a second. And the proof sizes are actually comparable to the best known blind signatures or post-quantum blind signatures as of today. We're in some sense 2x worse or something, but you're not paying for nothing. You are getting significantly more features through this approach, and you can also put in more work to reduce the proof size. Okay, so what is the high-level overview of our strategy? it's a two-pronged effort. What we're going to do is say, look, let's just start with dilithium. It's been proposed to be standardized, so hopefully it's secure. And what we're going to do is make it ZKP friendly. And we're also going to use ZKP friendly hashes. We use Poseidon. And we're also going to choose a proof system which is post-quantum. But we also need some properties from this proof system, which is that we need to be able to match the arithmetic in the proof system with that of dilithium. If that went over your head, it's okay. It's just we need to use a very specific field. And what we're also going to do is when we're doing the ZK dilithium verification circuit, we're going to reduce it to simpler statements in order to reduce the prover work. Okay, so let's go over some details. What is the pipeline of these proof systems, right? So let's say you have your code. It's doing some complicated stuff. You're going to translate it into what's known as an arithmetic intermediate representation. Think of this as just a table of field elements, and you're going to say, oh, look, every row is related to the next row in a very specific way. And what you're going to do is plug in this intermediate representation to your favorite Stark library, and this is going to spit out a proof. The second part of this pipeline is actually very nice. People have written very, very nice libraries. We use Winterfell. It's one of my favorites, quite nice to use. Essentially, you would run one command on your terminal, and this part would get over. But the first part is really what's difficult, because this is actually, at the moment, crucial for performance. You need really careful hand optimization at this point. Strategies are, you reduce the simpler circuits, but you need to maintain same soundness guarantees. Okay, so let's walk through how the dilithium verification happens. So in the dilithium scheme, you have a public key, which is A and T. You don't really need to know much more than that. It's a matrix, a 4x4 matrix. Each entry is a polynomial. The signature is Z and C tilde. Z is a vector of 4 entries, again, 4 polynomials. C tilde is just a scalar of lambda bits, where lambda is the security parameter, let's say. So the first thing you do in ZK dilithium is you need to map C tilde to C, where C contains entries which are -1, 0s, and 1s. And you need the number of non-zero entries in C to be tau. And because you want this to be a uniformly random mapping, you use a Fisher-Yates style strategy. But when you use Fisher-Yates, if you've implemented this, you'll remember that typically you use rejection sampling in the strategy, but this is just a no-go for zero-knowledge proof systems. So what you do is you can actually move the rejection sampling to the signing part and avoid it in the verification circuit. The second thing you do is matrix multiplication of these polynomials. What you do is you just compute A times Z minus C times D and store it in W. Effectively, you should just imagine this as multiplying a bunch of polynomials. And a standard strategy is, let's not compute, but verify that the computation was done correctly. And you're just going to reduce it to polynomial identity testing. This is asymptotically even better than computing this, because polynomial multiplication, if you use FFTs, is going to take like O of n log n, if n is the degree of the polynomial. If you just use polynomial identity testing, you're going to do it in n. And in fact, it's also significantly easier to implement the translation to AIRs. Okay. Then you're going to extract the high bits of this W that you've computed. Again, same strategy. Instead of actually computing, you're just going to check that the decomposition was carried out correctly. And finally, there's a part which is the hashing. So we use the Poseidon hash here, again, because it's just ZKP friendly. And you hash the public key, the message, and these high bits that you extracted, and you check that it's equal to the C tilde that appears in the signature. Okay. And finally, there's a bunch of range proofs and so on that you also need to do, standard strategies that you use in zero-knowledge proofs. Nothing crazy there. Okay. So this is a high-level pictorial diagram of how the AIR looks. I've omitted a lot of details because it's significantly more complicated than this. But what happens is we have a main table and an auxiliary table. The auxiliary table is on the right side. I'll get into a moment as to why I've separated the two things. But the idea is, you do the computation of different things in different parts of this table. The figure is actually roughly to scale, so you also have an idea of how expensive each thing is and how much resources you're dedicating to each of these things, and where is the bottleneck. So the hash and ball turns out is the widest thing because you really need large amount of memory to actually implement this. We tried, but we weren't really able to reduce that. Then, in this second green phase that I've written, this is this matrix multiplication and hashing phase, where you're going to store your polynomials on the left, do a bunch of range proofs, and you're going to check that high bits was decomposed correctly, and then you're going to do the hashing in the third column. So when you do polynomial identity testing, you actually need a random coin, or just a random field element on which you evaluate your polynomials. So the question is, how are you going to get this? What's actually happening here is, in this main table, you first commit to the polynomials, you do fiat shamir, you get a bunch of random coins, and then that's what you use to do the evaluation in this auxiliary table. That's why I've done the separation. So the evaluation of these polynomials happens actually in this auxiliary table. And of course, you just do the checks on the bottom, and everything works out. And this red areas is because we need this table to be a power of 2, because you need to do FFTs, and those red areas are just unused. If you're doing more general things, you can use that. There's actually a demo that we have up running at zkdilithium.cloudflareresearch.com. You can go try it out, scan a QR code, press start, and things should work okay. If it doesn't, please let us know. We'd like to figure out why. There's code available on GitHub. If you can't remember my name, it's in the paper. So takeaways and future work. This is something that I want to spend a little bit of time on, because with the migration to post-quantum, I think more people should hopefully start looking at these things. So first, post-quantum anonymous credentials are now semi-practical because we were just able to throw a proof at it, essentially. The second point is that, carefully tailoring your zero-knowledge proofs to the circuit that you're trying to prove can perform surprisingly well. And it's good to get estimates just by saying, oh, what happens if we just throw a naive proof at it? But you can't ignore the fact that if you put in engineering and time into it, you will perform significantly well. And if you want a bench line or a base mark, you need to put in that work and see, okay, if I'm going to design specialized protocols, this is at least how good they should perform. And something that I hope people look into, and hopefully we can look into as well, is designing post-quantum signatures for proof work, specifically for proof verification. Because we just picked up dilithium, right? And we just picked up ZK Starks. We didn't design these things. We modified them enough to make them fit together well. But if you could just start from scratch and design signature schemes with proof verification in mind. But maybe the trade-off is that signing is worse or verification is worse. But you can prove knowledge of a signature. That would be very, very cool. And vice versa. Design your proof verification with signatures in mind. We would also, at some point, like to have some formal verification of our AIR translation, which translates the ZK dilithium code into AIRs. There's more details and new ideas for rate limiting that we have in the paper. You can find it on ePrint. Thank you.
Thank you very much for the presentation. Please go with a question.
Yeah, so there was a talk yesterday that has something about the lattice-based proofs, which may be of interest, but that I don't know anything about. So my actual question is, why do you care about post-quantum soundness here? Why not? I think I could do this in 400 constraints in an R1CS ROS16 proof, and like hundreds, not thousand, 400. So I mean, why do you even care about post-quantum sound? I mean, eventually it might be important, but like now, if you want to deploy it.
Right, I agree. So obviously we don't have to deploy this right now, because maybe in the case of blind signatures, you can wait to migrate. But one thing is that if you don't start the work now, you can't really expect to magically get really good signatures in the end. Hopefully that answers the question.
Thanks for your presentation. I have noticed that you use the range proof. I guess it is zero knowledge too. So you do a post-quantum work, but as far as I know, the most well-known range proof, blade proofs, is not post-quantum. So what's the concrete range proof protocol you use?
We don't do anything smart with the range proof. We just do a bit decomposition and show that you can actually put it in some range. I think maybe what you're referring to is like specialized proofs for the specific task of range proofs. We can't really use those because we actually have a lot of other complicated stuff going on, which is like hashing and stuff. So we really have to use a range proof which fits in well with ZK Starks, and we just do a simple bit decomposition because that also didn't seem like the bottleneck in everything else that was happening. So we just didn't really put too much attention there.
Oh, okay. Another question.
Sure, sure.
I noticed your security level is 115 bit. This may not be as common as 128 bit and many others.
Right.
So what is the reason? Is the parameters for ZK Stack like the number of rounds in the ZK protocol or the field choice or some other reasons?
So, I mean, that was just a number that we chose because it was also coinciding with the dilithium parameters. But you could just make more queries. It's going to shoot up the proof size by like maybe 10 or 15%. You should be able to get up to 128 bits as well. Okay. That's not a bottleneck here. You can just change one number in the code and shoot up to 128 bits.
Okay, thanks.
You mentioned rate limiting. Can you say something about what you're doing there?
Right, yeah. So details are in the paper. Unfortunately, I didn't have time to go in. So there's an IETF draft, or I'm sorry, I don't know the exact word for it, but there's something in the IETF about rate limiting. And this is actually something that's going to be deployed by Apple, Cloudflare, and Fastly. What they do is to implement rate limiting, they introduce a third party called an attester. When you use anonymous credentials, we actually show that you can remove this third party, and it's just a significantly better trust assumption. And when you have these three parties, you need non-collusion assumptions. The idea is that this attester is going to sort of maintain a log of how many queries and how many tokens you've obtained. What you can do is with anonymous credentials, the client itself is going to maintain a table of how many tokens they've obtained and give a proof that, oh, look, in the last epoch, I only obtained 10 tokens. If it's an 11 token, you just can't prove the constraint. And that's how we remove this attester, roughly. Hopefully that answered the question.
We have time for a really small question. Okay.
Small enough. So with Privacy Pass in particular, it's about bot prevention, and another solution to bot prevention is kind of like proof of work. Obviously, like I say, I can have someone do a small hash and prove that they have some that makes it costly. I guess if someone has a quantum computer and they're using the quantum computer to produce fake tokens, it seems like they're basically doing more work than it would be to like break the CAPTCHA. I'm kind of curious. This is not like, obviously we need anonymous credentials for a lot of things. I'm curious about your mental model about this particular problem, or if you're thinking about your work in terms of like this particular problem or more broadly.
I agree. If breaking CAPTCHAs was really all you were interested in, then maybe you don't want to use a quantum computer for it. But I think the work, in some sense, Privacy Pass, if you view it as, oh, the problem of CAPTCHAs, it's not as interesting. But I think, the primitive is interesting outside the context of CAPTCHAs as well. And so it just makes sense to build more efficient primitives, just a Privacy Pass primitive for these broader applications. Just anonymous authentication, I think, is just a very cool thing that you would want a post-quantum version of, irrespective of whether it's for CAPTCHAs or not. Like maybe you could think of something like, oh, I'm just trying to log into my company's whatever system, right? You could use potentially anonymous authentication if you want to hide the logs and not really check whether your employees are doing your work and so on. But that's an option as well. Yeah.
Yeah, this is really cool work. Thank you.
Yeah.
Okay, thank you very much. And now we have the award ceremony.